Díaz García. He's a postdoc now at the Academia Cínica del Instituto de Astronomy and Astrophysics in Taiwan. He was doing the PhD in the Fecha. He was working mainly with the analysis of the Alhambra data, in particular related with the study with the galaxy evolution. He has continued this line of research in the new position at the Academia Cínica, but now he's also opened a new area of research related with lensing study. In this talk, he will be talking about the galaxy evolution, in fact, and with lensing study in the JPAS survey. He's very active member of the collaboration, so he will present new results that has not been so before. Okay, thanks.
Well, hello everyone. First of all, thanks for attending this seminar, and thanks to the organizer for giving me the opportunity to give this seminar here today. And of course, thanks to Rosa, who invited me to be to come here to Instituto de Astronomía de Andalucía during the next month. So, well, during this seminar, I will present mainly some results that we are obtaining in the JPAS collaboration, especially focus on galaxy evolution studies and with lensing studies, because are the groups in which I'm more active. And also remember, well, as many of you know, that during the next year, the JPAS survey is going to start, and it's going to observe more than 8,000 square degrees of the sky, but with a very nice new photometric system that is composed of 56 narrow bands that is also complemented with another 4 broad bands. And in the meantime, and and before Christmas, the JPAS collaboration also made publicly available JPAS-like data that we refer as mini JPAS, that I'm going to present a bit later. And during this talk, all the results that I'm going to present are the result of the analysis of this set of data. But more focus, especially in the work that I have participated or collaborated in a more active or less active way. Well, let's start. So, at present, there is an increasing number of multi-filter surveys such as Combo, 17 Cosmos, Alhambra, SARS, JPAS, also HSC, that have a main common feature, that is that they take images from the sky using photometric filters to observe the spectral distribution of all the sources that are in the sky. So there are some differences between these photometric surveys that, and some of them are especially the photometric system or the filter set that they are using. Some of them are using broad bands, some of them are using narrow bands, and some of them are using a combination of narrow and broad bands, like such as JPass. So in practice, especially for these surveys that are using narrow bands, these ones are the spectral energy distribution that we can retrieve from these objects is halfway between classical photometry and spectroscopy. And also depending of the one of the other differences between surveys is also the spectral range that they are observing. But usually they are ranging from ultraviolet to infrared. Especially these ones are larger and cover more area of the sky, are already demonstrating to be an excellent data set to explore different topics in astronomy owing to the advantages that they present. So one of these advantages is that they don't present a selection bias other than the depth of the survey, because you take a picture of the sky and there is no pre-selection of sources to retrieve the spectral distribution of the objects. The other one is usually they don't present systematics in the flux calibration, because every of the bands are calibrated independently each other. Usually also using the same telescope and a fixed observational time and using the same camera, they go deeper. And the photometry, the aperture for the photometry is defined for every of the sources. So this means that there is no aperture bias in the flux measurements. And another one is that when you are taking images from the sky using in photometric surveys, we can also retrieve a photospectrum for each of the pixels in the sky. That this allows, for instance, to study when the sources are very close to us, to explore spatial resolve studies. So owing to all these advantages, there are many people that are working in many different topics, usually in the collaboration in this, because also usually are very large collaborations. For instance, for JPass, there's a very big group that is involving galaxy evolution studies that is focused on galaxies properties like stellar populations studies, or also to the stellar populations of galaxies are higher redshifts, AGNs, or black holes, but also for cosmology. For instance, studying baryon acoustic oscillations, quasars, lensing, galaxy clusters, etc. Of course, also for stars and for transient objects. During the rest of the talk, mainly I'm going to focus in stellar population studies using the mini JPass survey that I'm going to introduce now, and also weak lensing studies. Well, so now, very briefly, I'm going to introduce the JPass survey for the people that is not related with this survey. But if someone is interested also in more details, you can find everything here in the paper of Benitez et al. 2014. And just to summarize, one of the most important features for JPass is the area that is going to observe, that is going to be larger than 8,000 square degrees. The depth for the images in the R band, because the R band is going to be the detection band, is going to be magnitude 24, and for narrow bands it's going to be around 22.5. All these definitions were estimated as assuming an aperture of 3 arcseconds up to a 5 sigma limit. And here in this plot we can see the footprint of JPass in the northern hemisphere on the left panel, and on the right the footprint in the southern hemisphere. Well, the telescope that is going to perform the survey is the T250. This telescope is in Observatorio Astrofísico de Javalambre in Teruel, Spain. And one of the main features of the telescope is that the main mirror has a diameter of 2.5 meters. The field of view is really huge. The diameter is 3 degrees, and the average scene expected for the observations is going to be around 0.7 arcseconds. The camera, here we have a picture of the camera, is composed, it's called GPCam, and is composed of 14 CCDs with a pixel scale of 0.23 arcseconds per pixel, and as well the field of view of the camera is really big, and is around 4.2 square degrees. If you need more details about the instruments, for instance, in the official web page, you can find many of them. And one of the most important features of this survey is the photometric system, as I mentioned it before, that is composed of 56 bands to map the spectral energy distribution of all the sources in the sky. It's composed of narrow bands with a full width half maximum of 145 angstroms, except for the bluest and the reddest band, that also are complemented with slow broad bands, but here are not plotted. Well, here we illustrate how we will see LRG, the spectral energy distribution that we retrieve for LRG observed with this photometric system. And thanks to the features of this photometric system, one of the great parameters that we can retrieve from the data is that we are going to retrieve very accurate photorecipes. In particular, it's expected to have more than 100 million galaxies with an accuracy in photoreceipt of 0.3% and 1% for more than 300 million galaxies. As I mentioned before, the JPass survey is going to start this year, but in the meantime, the JPass collaboration made a publicly available first data release that is called Mini JPass, which goals are mainly to prove the potential of the survey, and also to explore data validation tasks to check the high quality of the data. This Mini JPass survey is centered in the Aegis field, and therefore it overlaps with another surveys like Alhambra, HSC, CFHTL, and EGS. All this data, the catalogs can be found in this link. But there is a little difference between the Mini JPass survey and JPass survey, and it's that the camera that they use to perform this survey is different. The main difference is that this camera has only one CCD with a field of view that is smaller. And finally, after masking all the bright objects, all the problematic regions of the images, that is mini JPass is composed of 4 pointings. The total effective area after masking everything is 0.9 square degrees. One of the first data validation tasks that I performed when we had for the first time this data set, it was to compute the completeness of the catalogs. To do that, also I collaborate with Carlos López San Juan. We will see later his results. And to constrain the completeness of this of mini JPass, we took advantage that of the other surveys that overlaps in this region. In particular, we use HSC because HSC is much deeper than mini JPass, and also because I'm also a member of the collaboration with HSC, and this way it was much more easy. So finally, we decided to use HSC to use it as a reference to constrain the completeness. And how do we compute this completeness? Well, we compute the fraction of common detections between these two surveys, HSC and mini JPass. And to do that also, it's worth mentioning that we divided the sample in extended and point-like sources, and also we compute the completeness for each of the pointings because the observational conditions in each of the pointings were not the same. So just to check if the depth of all the pointings was the same or not. To do that, we went to the images, and we select for each of the pointings all the sources that were within the window frame, and we remove all the sources that were close to bright objects or problematic regions. The next step, we remove also the overlapping areas. And finally, we select all the common detections in the images. And we parameterize to get an analytic form of the completeness. We parameterize this fraction of common detections as a function of R of the R magnitude, because it's a detection man. And we fit it to a Fermi distribution in which we took into account the photon uncertainties in the photometry, and we introduced a new term to account for systematic discrepancies between both surveys. Because, for instance, there are differences in the observations between HSC and mini JPass that are related to the scene and the blending. So, as a result, we obtain 8 completeness curves for extended sources, for point-like sources, and these ones were for each of the pointings, okay? And as a result, we obtain that the observed fraction of common sources are the red dot for extended sources, and for point-like sources, the blue ones. If we remove this term to remove the systematic discrepancies between both surveys, we obtain these shaded regions, okay? And the DAS curves are the completeness curves. As a result, we obtain that for extended light sources, the completeness limit is around magnitude 22.7 in AB and auto magnitudes, and for point light sources, as expected, the completeness goes towards finer magnitudes. Just to check that also these results are working well, let's say. As a second check, what we do, it was to collaborate with Carlos López San Juan to compare the completeness curve that we obtain using real data with the completeness curve that we will obtain injecting synthetic sources. For this study, Carlos introduced synthetic galaxies from cosmos and different PSF that were computed using the real mini-JPAS data. And as you can see, the estimations for the completeness, they were consistent for all the pointings for extended and for point-like sources. And also, it's worth mentioning that for the pointing number 1, we found that this pointing was deeper than the other ones because a lower sin. Also, it didn't work too much in this comparison. So this work was mainly led by Andre, Rosa, Enrique, Paco as well, in which we compare the colors of the common sources in mini-JPAS with HSC and also with slope. And we found that the colors were consistent with the colors provided in mini-JPAS after comparing with HSC and slope. Well, during the next slides, I'm going to present the main works in which I was collaborating within the JPAS collaboration, specifically in the galaxy evolution studies. At this point, I would like to mention that that mainly I was working in set-fitting techniques, especially to obtain stellar population properties of galaxies from mini-JPAS photometry. It's also remarkable to say that within the JPAS collaboration there is not a unique technique or set-fitting technique to retrieve all these parameters, and there are several groups. Also, the number of groups is increasing with time, that we are using our proper techniques to explore how to determine in an accurate way the stellar population parameters of the galaxies in JPAS. So, for instance, one of the codes that we are using is SMAFIT. That is the code that I performed during my PhD at CEFCA. Also, we have the Seagull, that is mainly the code that is used in Rosa. And also All Star, that is the code that is developing Roberto Cid. Also, I mentioned that for photoRECIF there are another codes like LEFAR. And for instance, Antonio Caballero is using it to provide the photoRECIF in the catalogs of mini-JPAS, but there are another groups from Estonia, principally led by Antti Tam, that also they are developing new codes based on machine learning to determine the photoRECIF for JPAS. So here, to illustrate, I saw as a feat performed by Rosa and Roberto, I think, to explore the capabilities of JPAS to derive, especially resolve stellar populations. So in this case, they use manga spectra that were observed in mini-JPAS. The spectra from manga is the gray line. The black dots are the observed JPAS spectral energy distribution, and in red is the fit using two different codes: the code base Seagull and All Star. And the black stars illustrate in this case the age that they obtain for different regions of the galaxy using for manga, in this case starlight. And we can see that that for this case, JPass is adequate to retrieve stellar population, and also to carry these studies in spatially resolved galaxies. So also I started to use the code MAFIT to retrieve stellar population studies. This mainly I developed this code during my PhD using Alhambra data. So for JPass it was very easy to extend the code, and I ran the code using MAFIT and Bruthal and Charlotte SSP models. With these models, the code built composite stellar populations models, in this case 2-bars models, and it compares the photometry from mini JPass with the prediction from the models to retrieve ages, metallicities, stellar masses, extinction, and luminosities. As a result of the analysis, also we explore how well can we distinguish quiescent and star-forming galaxies using JPass data. In particular, we started, we follow the work that we did for Alhambra, and we explore different color diagrams and stellar mass color diagrams to see how to separate quiescent and star-forming galaxies. As a result, we will have these panels. These panels are for mini JPass. Each of the panels correspond to a redshift bin. The x-axis is the color R minus the reddest filter in JPass, and the y-axis is U minus R. I selected these bands only because are the most closest ones to classical UVGA color diagrams. And as expected, we obtained that there is a bimodality in these diagrams. So that also means that the photometry is working well at first level, and the star-forming galaxies lie on the bluer parts of the diagram, and the quiescent galaxies will be on the R, actually, on the upper parts of this diagram. Here in the insets, we can see the histogram of the U minus R colors. And we can see here as well, very well, the bimodality of quiescent versus star-forming galaxies. And one of the problems that we, not a problem, but when we use this kind of color diagrams, as you can see, there is an overlapping region in which both populations overlaps, quiescent and star-forming. So typically, if we use this reference color diagram only, we would expect that there is a contamination on in the quiescent sample. But as owing to the great spectral distribution that we have in JPass, we can also retrieve the extinction of this of each of the galaxies. So we can correct these diagrams for extinction, and we can build the same UVGA color diagram, but now using we can build again the UVGA color diagram, but now the colors are corrected for extinction. That means that these are the intrinsic colors of the populations. And we can see that now the distribution of red and blue galaxies are more separated each other, and it's more easy to distinguish between galaxies that are intrinsically red and galaxies that are intrinsically blue. This result is also in agreement with the studies that we performed in Alhambra, that are in this paper. And if we don't perform this extinction correction, we would expect that the sample of quiescent galaxies can be contaminated at 20%, owing to the dusty star-forming galaxies that are typically concentrated to these limits. Okay. But as we did for Alhambra, we explored another diagram that is a stellar mass color diagram, but corrected for extinction, because typically in UVJ color diagrams, you are not taking into account the stellar mass of the galaxy. So you have galaxies populating with different masses populating different regions here that typically are concentrated. For instance, the most massive ones are here in the peak, but the rest of them are distributed around, and we are not taking these color cuts as a function of the stellar mass. So for that reason, we use these stellar mass color diagrams corrected for extinction as well, and we see that now we can retrieve very well the two populations, and also we can we can separate both populations using U minus R color as a function of stellar mass and also as a function of redshift, because although when quiescent galaxies are not forming new stars, the proper aging of the galaxy makes that the galaxies go redder and redder and redder with a lower redshift. The other interesting result is that now, as you can see, the number of galaxies between, it's more easy to see this here, the number of galaxies between the two peaks that are usually called the Green Valley galaxies, this number decreased really a lot after correcting for extinction. That means that a very large fraction of galaxies in the Green Valley are actually dusty star-forming galaxies that are not part of the Green Valley when we take into account the extinction. To complement these diagrams, Rosa was also studying how the stellar population parameters populate the different regions of the stellar mass versus color diagrams. Here we can see the color versus stellar mass, but without correction, correcting for extinction. And the left, the four panels show four different stellar populations parameters. The first one is the luminosity weighted age. This one is the extinction. This one is the decay time. This one. And we can see that typically the redder galaxies corresponds to, for instance, larger ages. This means that are older than the star-forming ones expected. And also we can see that the star-forming ones present larger extinction values. We can repeat these panels, but now corrected for extinction, and we can see that also these relations are much more clear. And here, for instance, for age, the result is very clear. And also, this is a result that we obtained in my paper of 2019, in which we also found, using Alhambra data, that the stellar population parameters are very well located in this kind of diagrams. So that means that, for instance, for for other surveys for which we only know a couple of colors and the stellar mass, these diagrams can be very useful in the future to make a prediction of the stellar populations with a lower resolution than in JPass. If we go back again to the question of the Green Valley, here well, it's more easy to see because I also did this exercise in Alhambra. Alhambra is deeper, is the area in comparison with mini JPass is much larger, so we have a larger statistic to see the effect. But later, for the JPass survey, we can extend this study with a much really higher statistics and with many more bands to constrain better the stellar populations parameter. But here we have again the stellar mass versus color diagram corrected for extinction. And here it's more easy to see that the fraction of galaxies in the Green Valley is really, really low. So these are the number density, the comoving number densities that we obtain for Alhambra. So this means that for JPass, when we have a very large area observed, we can create a very large sample of Green Valley galaxies, and at the same time we can retrieve the stellar population parameters of these galaxies to explore their properties, but also to set constraints on the on the quenching mechanisms that are affecting galaxies. For instance, this is more easy to see if we think that okay. If we imagine that the Green Valley is a road, and our galaxies is people that is at both sides of the road, each of the panels is a picture that we are taking. So if we take a picture regularly and we don't see many people crossing the road, and also the number of people on the other side is increasing, that means that the quenching mechanisms are acting very fast. If we see a lot of people, that means that the quenching mechanisms are acting very slow. And this is something that now we can explore very nice with JPass and also with cosmic time. So now the last topic in which I'm going to talk is weak lensing. This is a word that I started during my postdoc in Taipei, and as well as many of the people sometimes is confusing what's weak lensing, and it's not quite related to galaxy evolution studies. I'm going to do a very brief introduction, but basically the light, we can say that it's a key tracer of the geometry of the universe because it's sensitive to change in fluctuations of the space-time, okay, that are produced by gravitational fields. In the case of galaxy clusters, here we can see, for instance, a galaxy cluster that is changing the space-time. The light is blended by the potential well created by the galaxy cluster, okay, and this way, if we are on the Earth, we will see that this galaxy that is in the background of the galaxy cluster we will see that it's here when actually is here. So the blending factor is related with the potential well created by the galaxy cluster and is expressed by this equation. Basically, if this is this direction in which we see the the object is, we call it beta, and the real position, we call it alpha, theta, sorry, we can determine the gravitational field that is dominated by this galaxy cluster. Okay. In the weak lensing regime, we can simplify this equation by the Jacobian matrix, that is this expression. The two important points is that it's not working well. Is that this matrix is well expressed by two terms. One is the convergence, and the other is the cosmic shear. And for the weak lensing regime, these parameters are small. To understand what's convergence and what's shear, we have this cartoon. For instance, if we have this source, the convergence changes the size of the galaxy in the background, but it doesn't change the shape. However, the shear changes the shape of the background galaxy, but in weak lensing we have a combination of both effects. So how do we to define magnification in weak lensing is basically this equation that is directly in the weak lensing regime. It depends only on convergence. But why magnification is relevant in weak lensing? It's relevant because it allows us, it's a method that allows us to determine the mass profiles of galaxy clusters that are dominated by dark matter. And this measurement is also complementary to shear measurements. And the good point is that a combination of shear and magnification reduce degeneracy in the equations, and therefore a combination of both can provide a better reconstruction of the mass profiles in clusters that, as I just mentioned, this profile is dominated by dark matter. So what we call magnification bias effect, that is the studies that I'm developing to measure the weak lensing in galaxy clusters in JPass, is a combination of two effects from gravitational lensing that are in conflict. And one of the effects is the flux magnification. So if we have a flux limited sample, and this is the luminosity function that we have in the background of the cluster, the effect is that you move the luminosity function to the right, because you are increasing the size of the background sources and you are increasing the total flux. Okay? And the other effect is the area distortion, because we are lensing a region behind the galaxy cluster that actually is smaller than the one that we are observing from the Earth. That means that the other effect move down the luminosity function. If we combine both effects, we will obtain something like this. So if we integrate the real luminosity function, that is the luminosity function that we will observe around the cluster, that means in the field, and we compare with, the total number of galaxies in the background, this provide us a measurement for magnification. And as magnification depends on the convergence, we can determine the convergence, and from the convergence we can determine the mass profile. So what we measure observationally is as I just commented, the number of background galaxies the number of galaxies in the field. That means that regions of the sky where there is no galaxy clusters. And this parameter that is the cumulative confidence slope at the limiting magnitude that is expressed by this equation. As one of the limitations of measurements of magnification bias is that typically these measurements are very noisy. So usually we need to stack many massive galaxy clusters to have as a signal. As in many JPass the area right now is lower than 1 square degree, we cannot do that. But at least we can, at least we can estimate the density in the field and also this parameter S. This is very important also to know at least what's the typical density of background sources as a function of the magnitude. And here we have these numbers for different redshift. Lower redshift would be the blue curves and higher redshift the red ones. And expected, of course, at finer magnitudes, the number of galaxies in the field increases, and at higher redshift decreases. But also we are exploring another methodologies to increase the signal of this study. And for instance, we are thinking in studying how to determine the magnification effects. Instead of using the total number of background sources, using the shape of the luminosity function. Also, this is a project that I'm going to start during this year, and it's the determination of the luminosity functions and the stellar mass functions in JPass, using data from the JPass, using as well the stellar masses, luminosities that we are retrieving using our self-fitting codes. These luminosity functions and stellar mass functions are important for wing-lengthening studies, but they are going to be also very important for the JPass survey itself, because the peculiarities of this survey makes that, for instance, in the nearby universe, we don't have perturbed bias effects in the flux of the galaxy. That means that we are going to integrate the total flux of each of the sources. We can study also the evolution with redshift. As the area is so large, we can make studies related to cosmic variance, including luminosity functions and stellar mass functions. And also, owing to the large number of galaxies, we are going to have a very robust determination of the massive end of the stellar mass functions. And the last method, we are thinking in another third method, also for weak lensing, and it's a method that is called photoredshift enhancement, that basically is based on exploring the redshift distribution of background galaxies. So that, for instance, from the paper of Coupon et al. 2013, we can make estimations, and this would be the distribution of real galaxies in the background, and this would be the one that we will observe owing to lensing effects. But the question is that to perform in this study properly, we need a very high quality photoredshift, but for JPass, we know that we are going to do it. So these are my summary and conclusions, so I think that I'm a bit out of time, so do you have questions?
Thank you, Chris, for the talk. Before to start the question, I forgot to mention that he will visit in the IAA for 1 month. He will be here up to 7th of February, and he is visiting with the financial support of the Severo Ochoa project. So please question.
When you estimated different star forming rates for the same sample and then you saw some change, how significant is that? Because you didn't show any errors and the differences were very small.
Sorry, can you repeat?
When you estimated with different methods or algorithms, ages or star formation, that one. The right one. So you used, I guess, what's the different colors, for example? And so I thought you used the different Mudfit, Basil, Gal, All-Star, Lefar to estimate that, no? So because the differences are very small and you do not show any error bars, how significant are the differences?
Rosa, do you remember a number?
The error is so small that you cannot see because
so the error is
there.
Okay.
So in some of the methods they use a Bayesian approach. So that means that we estimated the standard deviation with respect to the median value.
are real.
Yeah. Yes.
These galaxies are in the very nearby universe. When you go at receive 0.3, 0.5, then uncertainties start to be large.
And maybe another very naive questions because I don't know nothing about lensings or. So if you see an image of an arc around a galaxy cluster, how can you tell immediately it's wake lensing or regular gravitational lensing, or you need to measure the properties of the?
It's an arc, it's a strong lensing. It's very close to the center. Weak lensing, individually, you don't see anything. It's a statistical property. It's you change because, think that, this is the effect of weak lensing even is more subtle than this in this one that in the cartoon. It's just a bit, you change the electricity. Imagine that it's a spherical source. Weak lensing is going to make it, is going to increase the electricity, but just a bit. One by one, you don't know if that's the real electricity of the galaxy or not. But when you explore the electricity of background sources around the center, you see that systematically, when you go to the inner part of the cluster, this electricity is orientated systematically around the center. When you go further, this pattern starts to disappear, and when you go out, you see that statistically the electricity is zero.
So
because
the same cluster can cause both effects, but further away. Okay.
Determine the mass profiles of clusters is much better to combine strong lensing and weak lensing effects, because strong lensing is very sensitive to the mass in the center of the cluster, but weak lensing is only in the outer parts. So also weak lensing is very hard to determine in the very inner parts, because basically in the background you don't have sources. Basically you have your BCG. So you don't have a space to make a statistical estimation of the mass. However, in strong lensing you need one galaxy. You have one galaxy, you can determine the mass in the center.
less than to Luis for the top.
Please tell us something more about the green body. Tell us something more about the green body. You've gone, and you mentioned the galaxy go very fast through the green valley. How fast do they evolve through from the blue to the red? And for a typical 10 to the 10 solar mass galaxy, what it take? Half a giga-year or what?
That we were thinking, because usually to provide these numbers, you need to assume any kind of model, a tau model or something, okay? And it's not easy to provide numbers, so we are still working, but more or less we estimate that could be below 1.5 giga-years. So, in fact, it's fast. But I don't know how much lower is this number, but it's in the order of 1 giga-year. But these estimations are based on tau models, and basically we are working on this. This is something that we were discussing.
You can see in the other plot where I show the property of the galaxy, where it is the tau value.
Yes.
There, well, or in the other. It is in the plot on the right, on the bottom right, where you see the tau value. This is assuming in a star formation history, a parametric star formation history, a delayed tau model. So that means that it's as smaller is the tau value, the event of the star formation decrease quicker. So you see that in fact on the upper panel for the red sequence the value the tau value is lower than in the green band. Sorry, in the blue cloud. So that's an indication of the value that you say around 1 giga-year, which is the value of the tau model.
Thank you, Luis. I have a question that maybe you have already answered, but just to be sure. In Alhambra, we used galaxies as each galaxy was a point, so we had the information for the whole galaxy. And in what you are telling here as well, if I'm not wrong, right? But I guess that you can extract some information in the sense of what Khalifa did, because at least for biggest galaxies in projection, you will have points, so IFU like as you said at the beginning. So for how many galaxies do you expect to be able to use that kind of information?
Galaxies, you mean? Do you know the number?
Well,
Because
in the Aegis field, it is around 20 galaxies, for which the resi is below to 0.05. And they have extended. They are extended enough to perform the analysis. So, but this is 1 square degree and a special field. So we expected that, of course, we will have, we will map better sample when we have a larger area of the sky. Thousands of galaxies, yes.
In terms of depth, as compared with Khalifa, how it is? I mean, do you reach farther away in distance to the center of the galaxies, or?
Could you pass the slide to the where we see the that's one. Well, here it is one example. This is a galaxy, a resi as say 0.06 or something like this. It is one of the closer galaxy, and we had the advantage that we have the manga data. it is not clear, but in the images that it is there are two circles that correspond to the 1 and to 2 half-life radio of the galaxy, and inside of the inner ring that you can see there, it is the pentagon, which is the field of view of manga. It's not clear in the image, but it is there. So that means that for this kind of galaxy, manga was not able to observe the whole galaxy, only the inner 0.1 half-life radio. This is one advantage, significant advantage for JPass, because we were able to go to at least two half-life radio, and extracting the information of the radial distribution of the property, but manga cannot do it. Of course, for the closer galaxy, will be similar in terms of spatial distribution to Khalifa, but the advantage is that Khalifa is only, well, it was a lot of galaxy, of course, it was more than 600 galaxy, but we will have more galaxy, and we will have the advantage to study the property of the galaxy, the distribution of the property of the galaxy as a function of the environment. That's something that can not be done with the Khalifa.
I missed just one thing. How good are you at separating AGNs from star-forming galaxies since I understood that this could be possible with the 56 filter set?
All the flags, so I mean, it's integrated stellar populations, but we are not including the AGN effects. So it's something that we have to include now. I don't know if
this could somehow affect your conclusions, your analysis on the Green Valley issue.
In Alhambra, we estimated that the EGN effects were mainly negligible, except, of course, the bright ones. For JPass, probably it's going to be more relevant, let's say. They are going to appear emission lines. For instance, the contribution to the continuum maybe can be sensitive in some regions of the photospectrum. So it's something that we have to do. For Alhambra, we didn't see any effect. But of course, yeah.
One advantage of JPass is that because the filter is narrow, we can measure the emission line. So this is the work that Hina is doing in his PhD, and he was able to distinguish, and also using machine learning technique to distinguish or to measure the nitrogen 2, the H alpha, oxygen 3, H beta. So we are able to build the BPT diagram with this data, and we can distinguish and to know which galaxy has an AGNs. Yes. So that means that when we miss all the different analyses that we are performing now, we were able to see how many galaxies have an AGN and how they can change or contribute to the fraction of galaxies that it is in the Green Valley. So, more questions or comments? Okay, thank you, Luis, for